that Rich April is on too from Colgate. So got lots of people from everywhere. So I guess we'll start.
Okay.
Thank you all for coming. And I'm very, very pleased to welcome Martha Buckwalter-Davis to give our seminar today. Martha is an Alfred native and went to Alfred University, graduated 2006. When she was here, she worked with me in the Adirondacks. We dug a lot of soil pits together, along with Mari and Rich and Yecha and other people. Martha then went to Queen's University and got a master's degree in geochemistry, and now works for Golder Associates in Ireland. And she's gonna tell us about, can we use mine waste rock for construction? What we will do is, if you're at home and you have a question at the end, type it in the chat and then we'll call on you. If you're in room lecture hall, Fred will call on you if you have a question, and we'll make it all work out. And I would ask if, is everybody muted, Nicole? Yeah, okay. So when we ask you to ask your question, when we call on you, you can unmute yourself if you're on Zoom. So I'll turn it over to Martha.
Perfect, thank you very much. So, thank you for having me here to give this presentation. I'm currently based in Ireland. I work as a geochemist for Golder Associates. I've been in Ireland for 7 years as of today. Today is the 11th of September is the day that we moved to Ireland 7 years ago. And so I kind of wanted to walk you through a case study of the type of work I do. And so I sort of picked one case study, but there's a fair bit of introduction at the beginning. And then I hope to chat with you at the end, and we can talk about if you have any questions. So I was very fortunate to grow up in Alfred. I always say to people, I had a really wonderful childhood. And I was also very fortunate from a young age to know that I wanted to be a geologist. I think that I've said that since I was probably in grade 3, like 8 or 9. And that came from playing in the creek behind our house in Alfred Station, my parents' house. That really led to strong interest in water-rock interactions, I think, in environmental work. So when I graduated from Alfred Elmond, I originally went to SUNY Brockport for 2 years and majored in water resources and geology there, but then transferred back to Alfred University to join Michelle for her Adirondack research program, which is a lovely picture on the left there. And that was a really great introduction to doing research. And I did an honors thesis, which was also a really good part of thinking about research and really good prep for graduate school, actually. After I graduated in 2006, my husband and I together moved to Vancouver, and he started a master's. And I had originally intended to start a master's in hydrogeology in Vancouver as well, but I took a year break before I started my master's, and I ended up becoming employed. And I started in mining because in Vancouver, that was what jobs in geology were in mining. So I went from East Coast geology, all surficial, sedimentary stuff to a hard rock sort of mining environment. And I actually ended up working for a consultancy, a mining consultancy that did a lot of environmental geochemistry work and other things, hydrogeology as well. And from there, I realized that geochemistry was where I wanted to be. So I went and got my master's with a professor at Queen's who had instructed a number of my colleagues, and still today, even my colleagues in Golder, we jokingly call her the Golder Geochemistry Farm Team. And I did my master's on some old tailings deposits around Ontario. So that's the picture on the right there is during my master's. So I do recognize that Michelle did say that this was theoretically meant to be a non-technical talk, and geology is a descriptive science. There's a lot of terminology. Many of the reports that I submit for my clients have 2 or 3 pages of glossary terms with them, and we use a lot of acronyms and things like that. So I do recognize that a lot of people aren't that familiar with maybe the mining cycle, which I wasn't when I left Alfred and moved to Vancouver. So what I would like you to understand, I guess, as we're talking today, is that when we mine an ore, which is basically rock that has what's considered economically interesting levels of metals, we process that ore, crush it up, do things to it to get the metals out. And then the very finely crushed leftover rock is called tailings. So that is one of the wastes that's produced from mining. And then also to get to the ore that we are interested in, we often have to remove overburden or what's called waste rock. Basically, waste rock is like, it could be mineralized, but it doesn't have enough, you know, zinc or lead or whatever in it to make it economically interesting, worth money to extract those metals out of. So that is another waste that is generated from mining. And then you could argue that another waste that's generated from mining is also the water that's impacted by contacting the mine, by contacting the tailings. And so I deal in all three of those things. Essentially, I do waste management for very, very, very large volumes of waste. You know, they say that one gold ring could create 80 tons of waste. And so this is waste management on a very big scale. So the consequences of mining has a lot of environmental consequences. I'm sure that everybody here is aware of that. So mines, a lot of metal mines contain sulfide minerals. We think of fool's gold, pyrite, and other sulfide minerals that we're taking out of sort of a deep underground environment or a place where they aren't exposed to a lot of water or a lot of air. We bring them up to the surface, and that results in hugely increased rates of weathering. So they get crushed. This makes more fines, which have a larger surface area, which are more reactive. These rocks start breaking down much more quickly. And in this picture on the right there, the visit I did many years ago to a mine in Peru, and you can see that orange scar through the mine pit wall is a vein of sulfide minerals that has oxidized, that has turned to rust, essentially. And so this, when we have these metal sulfides that react with water and oxygen, we get something called acid rock drainage. And that is essentially metal sulfide reacting with water and oxygen to produce sulfuric acid. And you probably know sulfuric acid is not really that great. It has a low pH, it's environmental consequences. And these reactions are catalyzed by bacteria. So I won't get into that, but there's a lot of biogeochemistry aspects as well. So I've just shown this picture here. That's a sample of a limestone rock. And those little lovely crystals that you can see in it are pyrite, metal sulfides. And so we have an environmental impact from acidity, from metals that are associated with the rocks, and we can also generate salinity, which is high sulfates, and this can also produce sort of sludgy material, and that's all part of acid rock drainage. So we're putting natural rock in an unnatural environment, essentially. These mine wastes undergo these reactions. And this lovely picture here is a shale quarry that I do some work for here in Ireland. And the shale had a lot of pyrite in it, and as a consequence, it is generating pH 2 water, which is about the acidity of your stomach acid. That color is coming again from that sort of reaction that generates rust. So these environmental impacts are going to vary, but we can also have essentially, sometimes this acid rock drainage can be neutralized by what's called, by things that have neutralization potential. So We are interested in rock types that could react with these acids, such as carbonates, limestone, and they can help ameliorate these low pHs. And so when we are talking, as geochemists, we're interested in rocks that are going to help with neutralization. And the best neutralization is provided by carbonates, calcium and magnesium carbonates, rock types such as limestone and dolomite. So that reaction there, we're seeing carbonate react with, this is sort of a simplified reaction, but carbonates react with iron sulfides to produce sulfate and iron hydroxides. And it's essentially, the reaction is a neutralization by an acid and a base. So if you combine baking soda and vinegar, it fizzes. And that's what you get when you combine carbonates and sulfuric acid. So for a long time, we were really interested in acid rock drainage. We thought, oh, we definitely don't want that. But as the industry has moved on, we've recognized that metal leaching, which is essentially, metals in environmentally significant quantities, can occur in acidic conditions as well as non-acidic conditions. So we can get poor quality water from mines even if the mines aren't generating acidic drainage. And there's some minerals like arsenic and zinc that are actually soluble under neutral pH conditions. So even if we have carbonate reacting with our acids to help give us a more neutral pH, we can still have potentially poor quality water. So metal leaching, it doesn't just happen from mining. It can occur naturally as a consequence of exposing rock to oxygen and water. So we sort of talk about a number of different mine drainage types. We have neutral mine drainage. We have saline drainage at higher pHs. They might not have as high of a metal load as acid rock drainage, but these poor quality waters can happen in all pH environments. And so if we think about acid rock drainage, very high metals, high sulfates, they absolutely need to be treated because acidic pH is it just absolutely destroys environments. Neutral mine drainage may have lower metals that can be treated perhaps more easily than acid rock drainage because we don't have to provide quite as much neutralization. And saline drainage is really, we're interested in removing sulfate, and that's a big issue for a lot of mines. Sulfate especially is, we don't want to have sulfate in drinking waters or for other ecological receptors essentially. So acid rock draining and metal leaching are bad. We know that. They have significant negative impacts on the environment. They can be toxic. Those metals can be absorbed by plants and animals. And importantly, essentially, like once acid rock drainage starts, it can persist for hundreds of years until sulfides are completely oxidized. And it takes, these reactions can carry on. And once these reactions start, the chemistry loves to basically keep itself going. It can be very expensive to manage, and small little quarries or mines can have to deal with acid rock drainage for a very long time post closure. And so there's a lot of work, there's a lot of cost for the owners of such sites. So our goal has to be to prevent it. Our goal has to be to prevent acid rock drainage and metal leaching. An ounce of prevention is worth a pound of cure. As you can see here for my client, they will, for a small quarry here, they will spend a huge amount of money to treat this poor quality water, which they can't discharge. So that's the work, that's essentially the work that I do as a consultant, and is geochemical characterization. It's looking at the chemical elements in rocks and soils and water and how they'll impact the environment, and specifically the sort of niche field that I'm in, which is a fairly small field, is predicting, controlling, and managing mine drainage chemistry. So understanding the chemistry of a mining system, of a mining deposit, will impact the project from very beginning to very end. You know, we're looking to, it has huge consequences over the life of the mine for getting regulatory social license or social license permission to operate, to prove that they're not going to cause harm to the environment, and also when they close that they're going to adequately manage the systems, because these are naturally mineralized systems. We are interested in them because of their mineralization, because of their metals, because of their sulfides, but they have an environmental consequence as well that we recognize is important, that protecting the environment of our mine, around our mines, is important. So some of the work that I do is prediction of acid rock drainage and metal leaching, and then that can integrate into support for mining services, you know, including water resources, mine waste management, going through regulatory permission, and then we may do hydrogeochemical modeling as well. With that, I wanted to take this opportunity to kind of walk through a little case study of a project I worked on recently, and then maybe we'll sort of explain some of the processes or how we get started on these kinds of projects. And so we have this as a client. They're an existing mine. They've been in operations for many years. They are an underground mine, not an open pit mine, and they are developing further into an underground system. So they're going deeper, they're going further, they're generating more waste rock. And because the mine is expanding, they also need to expand their tailings management facility, which is where they keep that ground up rock and water from the processing of the metals. And that's a photo there of their TMF, the tailings management facility. So there's a huge requirement for earthworks as part of building this system. And so they would like to use the waste rock as aggregate material for construction. So the existing limits on their license sort of specify that they cannot use waste rock that has higher sulfides. The limit that's on their license is sulfide sulfur content of greater than 1%. So that pyrite mineralization that I was talking about can't be higher than 1%. So they can't use it for construction without specific approval from their regulator. So what they know from testing already is that their rock does have a sulfide sulfur content of greater than 1%. And so they were looking to understand the environmental risk essentially and demonstrate that it wasn't an environmental risk and get permission to use this material. Why do they want to do that? Well, the only outlet for waste rock right now is for them to put it back underground. So they take it out, they get out the metal that they want, and then they put it back in to backfill, or they have to stockpile it at the surface. They have to take it out to get what they want. So if they put it back underground, they are also taking some of their tailings and using that as backfill material in an underground setting. So if they do that, if they have to use waste rock to backfill, then they can't put as many tailings. Then they have to put more tailings into that huge pond of tailings water. And thus, they will have a larger requirement to store tailings above ground. And also using waste rock for construction provides a more sustainable solution than sourcing virgin aggregates, essentially. So if they're gonna have to buy rock anyway to do this huge earthworks project that they're doing, you know, to lay down for roads, to put into berms and walls and things like that. So could they use this as an aggregate, and then they don't have to go quarry, you know, new rock out of somewhere. So that's a very sustainable solution, right? Is using a waste to as a product essentially. So I've sort of explained this a little bit already, but just to show sort of the development process, they tunnel to access the mineralized zones and produce ore. And then the waste rock, which in the case of our client, they usually consider less than 3% sulfides to be sort of waste rock. And they're basically making these stopes. The word stopes is sort of underground rooms that they're taking their ore out of. So they really, there's a, this is the argument for them to try to find a more sustainable use for this waste rock so that it doesn't require management at the surface as a waste, but rather it sort of becomes a product. So the first step of our process was looking at their existing stockpile of waste rock and collecting samples. So we used a British standard for testing stockpile, for sampling from a stockpile. So climb all around that stockpile, grab increments by increments, I mean subsamples essentially. So grabbing a few kilograms of rock from different points around the stockpile. And then when we have about 15 kilograms, we mix that 15 kilograms of rock up, and then we use a process called coning and quartering to homogenize and reduce that sample to the amount that we need to send off to the laboratory for testing. So this, it may sound a little bit ridiculous to do all this, like why can't we just go out and grab a piece of rock? But the point of doing an exercise like this and sampling in this way is proving sort of that we have gotten sort of an averaged, homogenized sample, that we aren't sort of selecting rocks that we think are going to meet the characteristics that we think we want. We're trying to sort of randomize our sampling approach. And so you can see that picture of me and Fieldberger, that's not from this project, that's from a project many years ago, but I like it because it shows the coning and quartering procedure. We pile it all up in a pile, and then we break it into quarters and then discard random, basically opposite quarters to get a reasonable sample, essentially. So then we move on to sending those samples off for laboratory analysis. And this is the suite of testing, and I'm going to go through this, so you don't have to know this right now. But we use a specialist Canadian laboratory because a lot of geochemistry work done in Canada. So we're looking at the chemistry of the rock. We're looking at the mineralogy. What are the minerals that make up the rock? We're looking at something called acid-base accounting, which is a specialized suite of laboratory tests to estimate basically acid generation and acid neutralization. And we look at also doing some leach testing, which is reacting the rock with water or acid to estimate that metal leaching. Are we going to produce metals in water that are at levels that are too high, essentially? So we're looking for that static. Yeah, we're essentially looking, this is sort of the first step. How much acid is it going to generate, and how much acid neutralization potential does it have? We make a lot of assumptions at this beginning stage. This is not the be-all, end-all of the test, but this is where we get started. So our acid-base accounting suite looks at basically chemistry that influences acid neutralization, which is our carbonates, and sort of titrating the sample with acid to see how much acid it consumes. That measures the neutralization. And then we look at those sulfides that I've talked about before. So we make calculations from that data to say, this is what the acid potential is, this is what the neutralization potential is, this is what the carbonate neutralization potential is, because we really like those carbonates. Carbonates are the minerals that we're most interested in for neutralizing acid. And then we make measurements by subtracting those neutralization potentials from those acid potentials, or expressing them as a ratio to each other by dividing acid potential by neutralization potential, essentially. So when we're done with the data, when we get the data, we sort of use this to say, this is like our first pass. Okay, does the rock look to be acid generating or not acid generating by these sort of benchmark values that we'll use. And I have a reference for this table later. But basically, these are sort of the screening criteria that we're going to use to say, yes, is it acid generating? Yes, is it non-acid generating, essentially. So this is what we get. These are the results that we get back. We can see that our total sulfur is most of the samples are low, but we have this one sample here that looks really high. Why is that total sulfur so high? We can see the neutralization potential, and then we can make those calculations of those relationships between acid potential and neutralization potential. And we really prefer to express these graphically. So I will start by looking at my sulfur content versus so we have the total sulfur versus the sulfide sulfur. And again, the sulfides are those ones that are the acid generating kind. We don't like those. So we'll see that for these samples, a lot of them are plotting on this 1-to-1 line. So essentially, most of the sulfur in these samples is sulfide. So, that's kind of what we expected. This is the kind of mine that it is. It just means that, we have to be aware of that. And then we take that neutralization potential that was measured by titration and that acid generation potential and plot them against each other. And then we essentially bin them based on those tables I was showing you earlier. If we have a ratio where there's 2 times as much acid neutralization potential versus acid potential, that we're saying basically there's twice as much neutralization as acidity. So we can be reasonably happy that we think that those are not going to be acid generating. If they fall between that 1 and 2, it's uncertain, but none of our samples were considered potentially acid generating. And then if we looked at that ratio of neutralization potential to acid potential versus our sulfide content, we can see that neutralization potential ratio goes way down as sulfide increases. So that the sulfide content is going to be a really big control on our potential for acid rock generation. The samples have a lot of neutralization potential, but if the sulfide values get higher, then we're going to have to start watching out for potential acidity, because it could overwhelm the ability of the rock to neutralize itself, essentially. We also did this test called a NAG test, and this is just an alternative test that was developed in Australia, where you basically shake the crushed rock sample with a lot of hydrogen peroxide. So hydrogen peroxide, H2O2, is a very aggressive oxidant. So it's like we're trying to estimate essentially the terminal state of this rock sample. So shaking it up, really aggressively oxidizing it, and then seeing if the pH, when we're done with that shaking, is acidic or not. So the acidic benchmark is essentially 4.5 pH. All of these samples are well above 4.5. So what that tells us is pretty good news that these are not acid generating samples. So essentially, the neutralization potential won't be depleted, so the system will retain a capacity to have a neutral pH, essentially. So, and we can also take that, what we call the leachate, the solution that's left by this solution, the solution that's left after we shake it up, we can analyze that for metals as an estimation of sort of the potential for metal leaching as well. So that's, again, sort of an estimation of a terminal state, like what's the worst possible water quality that we could be getting from these rocks. So we also do trace element chemistry. So the rocks are analyzed for the chemical elements that are in them. And what we do with these values that we get off of our samples is we compare them against an average crustal abundance. So these are values from literature to say, on average, this is how much silver, aluminum, or aluminum, as you say, arsenic, barium, etc., are in the rocks. And then what we're going to see is our samples elevated compared to them. And when we look, the reason that we do this essentially is to basically tell us what metals are potentially elevated in the environmental system. So if it's elevated, it doesn't mean necessarily it's going to be mobilized and move into the water and cause an environmental problem, but this is essentially like what we're going to look for. You know, we're gonna look, does it leach cadmium? Because cadmium is at least 6 times elevated above average crustal abundance. You know, is it gonna leach some zinc? Because the zinc is quite elevated above our average crustal abundance. Is it gonna leach lead, you know, antimony or selenium? So these are all, this is just sort of one of the toolkit items that we use to look at these rocks sort of at the beginning. So we do also send the samples for XRD mineralogy, so X-ray diffraction. And what we're looking for is acid producing and acid neutralizing minerals. So these are rock samples. We're very interested in knowing how much calcite and dolomite are in them. You know, they're a limestone sample, so majority of them are the calcite, which is limestone, is the largest by abundance. And then we're also interested in knowing what the acid producing minerals are. So the sulfides, we have galena, lead sulfide, there's valerite, zinc sulfide, we have pyrite, iron sulfide, and all of those are going to lead, potentially, you know, can lead to the acid problems that we were talking about. So all those things kind of are working together. And then the final piece in this, what we call our static test toolkit, is doing our preliminary leach testing. So our leach tests are to identify elements that are maybe of environmental concern, and doing like a short-term leach test can be an estimation of initial water quality. So we take like an uncrushed sample, we agitate it in water or a mild acid for a while, and then we analyze the water, and then we can compare the metals that are in that water to background levels or to local water quality limits. You know, for example, if we have groundwater criteria or surface water criteria in whatever jurisdiction we're working in, and that then we can sort of start to get an idea of what we have to be worried about. But it's important, really important for this kind of sample where you're just putting it into water. Sulfides that are not going to react in that shorter period of time. So it's not an estimation of final water quality by any means. So we did that, and then we basically, one of the things that geochemists like to do is put these into Ficklin diagrams. And so Ficklin was a researcher who basically identified that the elements zinc and copper, cadmium, lead, and cobalt and nickel are sort of diagnostic in mining settings. And he created sort of a binned table to sort of categorize water quality using the sum of those metals in water versus pH. So obviously, we really don't want to be in the ultra acid extreme metal category. We were delighted that these samples are in the alkaline low metal category. They're alkaline because it's a limestone rock. It's a base. So, but this is sort of a nice visual tool that we like to use. Now, I told you about the highly oxidized samples that we did, the NAG leachate, which were not acid generating, but those are more of an estimation of that terminal water quality, where we've oxidized all of our sulfides, and they have been reacted with all of the buffering of the neutralization potential that is ameliorating that acid. And when we did that, we have some samples falling into near neutral low metal and some samples falling into alkaline low metal. But we're very happy because we're in the low metal category, and we like to be in the low metal category. So our program of characterization, together with our client's data, demonstrated that the mine waste rock was not acid generating, even when the sulfide content is greater than 1%. So what we came to them, our client had pulled some samples, we've taken some samples, we put them together, we looked at them and we said, okay, the majority of our samples are falling into like a 1 to 2% sulfide range, which is above the limit that we're allowed to use it for construction. But even at these limits, the samples are non-acid generating and appear to have a low metal leaching potential. So we have, they're in limestone, they have abundant neutralization potential. So we basically said, please can we use them in the walls of our new tailings pond, the embankment walls, where they will be covered with clay and liner to sort of encapsulate them. They're in a controlled system where drainage is collected around the mining facility. What we're saying is we're using it in a controlled environment where we are limiting its exposure to water and air that could oxidize and weather that and cause potential environmental issues. And also we are capturing the water that is draining off of them wherever we use it, because we plan to use the rock fill sort of where we have random fill material here on this diagram. So we proposed to our regulator, can you please allow us to use it under these specific scenarios with a maximum sulfide content of 3%? The license limit is 1%. So we need a sustainable outlet for our waste rock. It saves us our underground voids for what we need them for. And the environmental risk under these scenarios is low. And they said yes, which was a really great result. So we were delighted with that. And we didn't have to move on to further work or further testing for this specific project. But I thought I would just show a little bit maybe of other types of tests that we don't always get the chance to stop at this stage of a project, of a geochemical characterization project. We often have to move on to kinetic testing. So I thought I'd walk through a little bit of those kind of tests just so you can understand how we sort of build these arguments and build up our data. So usually the majority of our projects, we do move from static testing to kinetic testing. And that may be because acid rock drainage has been identified, or there's metal leaching potential, and we know that our materials, our tailings, or our waste rock are going to require some kind of long-term management, and we need to understand better how they will react under field conditions. The conditions that we do for all those laboratory tests I just talked about are not necessarily representative of what it's like in a real life setting. In a mine could be in a very arid environment where there's not a lot of rain, or very different climates. So we use kinetic tests, which are basically tests where we react the rock with water to try to get information about leachate water quality in a short period of time compared to actual field conditions. So that may be a humidity cell test where we put the rock in a little cell and react it with water. We may put larger amounts of rock into like a big barrel and have them outside and collect the water that drains off of them. We may do column tests which we can saturate the rock with water and see what the rock looks like when it's saturated, how the rock reacts with water when it's always covered with water. And this also helps us because the rock is going to be in different conditions in a field setting versus being sort of crushed and tested in a laboratory setting. So there's a lot of reasons that we do this, but one of the main reasons is to simulate site conditions and to predict water quality so we can reassure somebody that we're not going to cause environmental harm, or that if environmental risk is in place, how we're going to control that environmental risk, essentially, how we're going to select those control measures, whether it be treatment or encapsulation. There's a lot of different things that we might do it, and we kind of have to prove it before we can get permission to do it. So this is a picture of humidity cells. I don't really expect to be able to go through all these, but essentially this is one of our first stops because we're basically putting the sample under alternating flushes of water and humid air to really try to flush it out and get information fast. And this is an example of data that we get from that. This is for another project, not the previous case study, but we may do this over 30 weeks or more. There's humidity cells that have been running for years, and we're gonna look at every week we get a measurement of pH and all of our other interesting elements, and we can start to look at how they're performing over time. And we can compare them against effluent water quality guidelines that are specific for our clients. So, is the pH too low? Is in this case, it's not meeting the pH criteria there in red. We may have some issues. And so that's what we use that data for. This is just an example of a column test that, again, it can be a little bit better for filling with water in a saturated setting, or percolating water through, dripping water through from top to bottom to see how water will react there. And then we have these field bins, which we put large volumes of rock into a barrel and sit it outside, and then we have to collect the leachate that comes out of that. And that is one of our best sort of field scale processes. And this is a picture of me putting together some field bins many years ago for a client in Canada. You can see we essentially crushed several hundred kilograms of rock by hand and put it in. It was as exhausting as it looks, actually, but it's one of our more interesting ways to get sort of that field information, collect the leachate out. So I'm probably going to skip over this because I'm running a little over time, but essentially all this is to say is that we're interested in taking prediction, we're interested in using our information to predict water quality. And we can use all of this drainage information, leachate testing, et cetera, to make water quality models and try to predict what the water quality will look like when the mine is operational or when the mine closes or things like that. And I could do an entire presentation on that. So modeling is a very complex exercise, but it's really can be a really important part of these projects. And this is just a common example. Application for modeling is pit lakes, which form after open pit mining is done, and the groundwater or the surface water is allowed basically to flood back into the open pit. And it can form very poor quality water if things aren't managed well. And we kind of need to prove that we're not going to create acidic pit lakes, because if birds land in them, then the birds die and things like that's not pleasant. So there's a lot of questions that geochemistry can answer. I've tried to just give a few today. Can we use this material for construction? Where will the impacted water go to? Where did this contamination come from? What happens to the quality of the water when we take it out of the mine? There's a lot of questions. that we can answer, and that's what we do for our clients, and this advice is really mostly for our clients, but we try to get this process started early in mining process, get to know the rocks, build up big data sets so that by the time they're looking to get permission to open a mine is a huge process. Opening a mine is a hugely expensive and difficult process. And due to the risks involved, the precautionary principle applies in the absence of robust data. So if I haven't done any geochemistry for my mine, I might have to assume that all my rock is acid generating, and that would be hugely expensive because I basically have to like seal it in a vault to keep it from reacting. So that's why it's good for our clients to do this. That's why, you know, many government jurisdictions encourage them to do this kind of work, understanding the environmental risks. And these are the sort of references or Bibles that I use. Most of the time, what's called the GARD Guide, the Global Acid Rock Drainage Guide, which there's a website, and then there's some really good Canadian references. A lot of the sort of masters of geochemistry are Canadian. That's how I got into geochemistry, is moving to Canada. And then if you are interested in being a geochemist, and not everybody who's listening is going to be, but take as much chemistry as you can. And then, you know, a lot of us come from geology into geochemistry, and then we have to learn a lot of chemistry, and there's a lot of value in really being knowledgeable about chemical processes. You know, most of us have done masters or PhDs, and in general, the specific type of work that I do is mostly in mining centers, you know, so here in Ireland, there's a few mines, and I also do work in Europe. I'm over here because I was recruited out of my master's to the office here in Canada, here in Ireland, but my company is a Canadian company that I'm working for here in Ireland. And yeah, the geochemistry motherland, in my experience, has been Canada. That's where I got started. And then I'll leave you with this. If you're not part of the solution, you're part of the precipitate, which is one of my favorite chemistry jokes. And thank you so much. And I'm sorry I went 5 minutes over. And I'd be really happy to take any questions.
Okay, I'm going to thank Martha, and we do have time, a little bit of time for questions. I just want to, one comment. I think this is such an excellent example of how she used both her geology and environmental science degrees. And I think I'm going to ask Fred if there are questions there in the lecture hall, and then we can see if there are any. Again, if you have a question on Zoom land, just type your name into the chat, and I will call on you after Fred's done with the people in the lecture hall.
Can you hear me?
I can hear you.
Okay, I'll pass on the mic.
So the case study that you showed today was a pretty specific example of how we could use these rocks. Do you think that in the future there's going to be more general uses for these rocks to try and get more out of them?
Yeah, I think there is a lot of people interested in also, you know, finding uses. Certainly in my experience in Europe, there's a large burden to prove that it won't cause environmental harm. And in doing that, it often requires essentially extensive risk assessment to say it's being used under specific scenarios. So like this material for this case study, it would not, the sulfide content is too high for it to be sold as a construction aggregate product to anybody who walked in the door. Like if, you know, somebody going to a quarry to buy crushed pea gravel for their driveway, this wouldn't meet the chemical conditions for that. So I think there's a lot of work going into finding more sustainable solutions for waste rather than just letting it sit in a pile somewhere requiring management for forever. But it really comes down to environmental risk.
My question was, why is Canada the geochemistry motherland?
Yeah, that's a good question. In my experience, there's a strong culture in the U.S. mining system too, but it's really embedded into, this type of work is really embedded into the process of getting permission to open a mine in Canada. And Canada in general is a very resource-focused economy. So mining is really important there. Is a larger sort of proportion of the GDP of the economic marketplace in Canada. So, and they have high environmental standards. So this specific type of mining, of environmental geochemistry for the mining industry has just really been developed a lot in Canada. But there are a lot of, like, in my company, there's a lot of geochemists in the US as well. And also there's small groups in other mining centers like Latin America, South Africa, and Australia.
Thanks, Martha. Senior seminar is going to sign out here because there's another class coming in here. So we'll leave room for other questions. But thank you from our
Thanks,
part.
Fred.
Okay, so we have a couple on the chat. What are some of the non-mining geochemistry projects you've worked on?
Well, I do, as you're saying, Michelle, like a mix of having an environmental studies background has been very, very beneficial for me, actually, in sort of flip-flopping between mining and non-mining, because mining is a very cyclical industry. So I do a lot of waste soil work as well. That's actually probably half my time or more is contaminated soils. So digging up sites for building high rises and the soil's been contaminated because it used to be a chemical plant or something like that, and characterizing that or remediating that or finding a landfill for that contaminated soil to go to. I do a lot of work around contaminated soils, which geochemistry absolutely benefits that.
Great. So next time we have you give a talk, you can talk on that.
Sure.
And Dr. Claire wants to know, do you deal with mining radioactive materials too?
I personally haven't done any uranium work, but absolutely do. Yeah, we don't, it's a different geochemical system, uranium, because of the way it behaves in the environment and its decay and things like that. But there are geochemists who do uranium work, especially, and also, there is, I personally haven't done it, but absolutely is an issue for uranium mines to do geochemical characterization and understand the risks of radioactivity.
Okay, and I'll ask the last question and then we can finish up. So on that project you talked about, and the regulator said it was okay for you to use the material that way. If ultimately that material does leak out some metals or acids, is the company liable for that?
If they contributed to a pollution event, then yes, if they essentially they would have to, if they were causing pollution, the way the legislation works in Ireland and in Europe is yes, they are. So that's why they have mitigating measures in place. Like the collection of the drainage water from the system and things like that goes for treatment. But a lot of that would also come down to demonstrating risk. So even if it leaked out, is it causing harm? Is there actually a risk to receptors? So hopefully that won't happen. We don't expect that to happen. But that they would indeed, yeah.
Okay. Well, then let's thank Martha, and next week we have another chemistry talk. Brennan Ferguson, who graduated in 2015, is a graduate student. She was a double major in environmental studies and chemistry. And she is actually going to be talking about radioactive, studying uranium transport across scales. So, but thank you, Martha.
Thank you. Thanks, everybody. I better go. Bye.
And thank you all for coming. It's so good to see so many people, and especially so many alums and community members.
Thank you.
Bye.
Thank you. Bye.